Hey, so this is going to be a presentation on what are called Napier's bones and his logarithms. Begin. John Napier, the man in question, was born in 1550 in Scotland, was born into a fairly wealthy family, which enabled him to pursue an education. Although, interestingly, the details of his education are not super duper clear. It appears that he entered into a school called St. Andrews, which seems to be kind of like a high school or like a junior college in Scotland. He entered into there. There is documentation that he entered there. There's no documentation that he graduated, no documentation of when he left, and there is some speculation that maybe after St. Andrews he was sent to mainland Europe to study at one of the universities there. Although, again, there's actually no documentation that he enrolled in any university. There's no documentation that he graduated from any university. So, kind of a mystery as far as how kind of clever, how he got to be so clever, and he was very clever. We mainly know today of John Napier due to his contributions within mathematics, although in his time he was actually better known for a Protestant treatise that he made or wrote titled A Plain Discovery of the Whole Revelation of St. John. And a couple of interesting points that I found about this treatise are one, in this treatise, he claimed that the Pope at the time was the Antichrist. And he also seemed to have found some discovery that the world was going to end between 1688 and 1700. So, as clever as he was apparently wrong about at least one thing. And yeah, it was not really until the later part of his life that his mathematical work became popular, and maybe even after his death that it became really very well known. His best known contributions to math include his bones and his logarithms, both of which were used as computational aids, as well as his influence in adopting the use of the decimal point. And he died in 1617. So the way that I kind of want to go through the rest of this presentation, I want to talk about both Napier's bones and his logarithms. I'm going to kind of go through Napier's bones fairly quickly. One, because I think it's easy to grasp. Two, because I want to save time for his logarithms, which is, in my opinion, maybe the more significant of his contributions. So around his time, there was kind of this need for speedy and accurate computation, especially of really large numbers. With astronomical science, they work with these huge numbers. Multiplying them can be very cumbersome. So there was a need to kind of simplify those computations, and that's where Napier's bones or his rods sort of come in. So he developed this idea that he would write down on these various rods. They really had nothing to do with bones. I think that the term bones comes from like some sort of mistranslation somewhere along the line, but the name stuck. So, anyways, his bones they show there are nine of them, and each of them shows like the first nine multiples of the numbers 1 through 9. So the vertical columns here represent the bones, and you can see just looking down each column, it just shows the multiples of whatever number is at the top. And his the way that he kind of used this, it was really an improvement on an already existing multiplication technique called lattice multiplication, which had been around for a long time, maybe even back as far as Mesopotamia. But his mechanism, his bones made lattice multiplication even easier. And the crux of his multiplication is actually that, or of using his bones, is actually that it breaks up any sort of complicated multiplication problem into smaller multiplication problems that are easy to compute, and then you just add them. So it's really just the distributive property. So for example, suppose that we wanted to multiply 497 by 72. The first thing that we would do is we would grab the 4, the 9, and the 7 bones, and we would lay them side by side. And then these rows of these bones, if we kind of sum along the diagonals, it actually shows what these multiples of 497 are. So 497 by 1, for instance, of course, is just 497. So what we're going to do in terms of 497 times 72 is we break this up into 497 times 70 plus 497 times 2, and we add those two partial products, and it gives us the full product. So here's kind of how that works in practice. We've laid out our 4, 9, and 7 rods. And the first thing that we want to do is we want to multiply essentially 497 by 70. Now the rods show 497 by 7. So we have to account for that factor of 10. And the way that we account for that is by we either at the very beginning you tack on a 0 or at the very end you tack on a 0. In any case, what we do is in order to do 497 by any one of these rows is we sum the digits in the row across the diagonals moving from right to left, which sounds kind of more complicated than it actually is. So here's the idea. If I want to do 497 times 70 first, since I'm multiplying by 70 rather than just 7, I'm going to account for that factor of 10, and I'm just going to write down a 0. Now I'm going to move from right to left through these diagonals, take a sum across the diagonals, and whatever that sum in each diagonal is, I just kind of concatenate that and prepend that to whatever number I already have. So I've written down my 0. I look at the farthest right diagonal, which is just this 9. Okay, I prepend a 9. So right now my figure is 9, 0. I move to the next diagonal is 4 plus 3 is 7. I prepend a 7, 790. I move to the next diagonal, and here's where a little bit of a trick comes in. 6 plus 8 is 14. So when you have a diagonal that results in a number, the sum of the numbers is greater than 9, you prepend whatever digit is in the ones place, and you carry whatever digit is in the tens place, you carry that over to the next diagonal. So 6 plus 8 is 14, so I prepend the 4 to my 790, so I have 4790, and I carry the 1 to the next diagonal. The next diagonal just has a 2. 1 plus 2 is 3. So what this is saying, put it all together, 497 times 70 is 34,790. And then, of course, we just do the exact same thing with the 2 row. And doing that, you see that we end up with 4 prepended by 9, prepended by another 9. So 497 times 2 is 994. So now we have these two partial products, 34,790 and 994. We add these together, and that gives us our full product. So 497 times 72 is 35,784. So we reduced the multiplication problem just to a fairly simple addition problem. And as you can imagine, if we can do this with multiplication, we can also use Napier's bones for division. And really the way that it works, you still have to do like the long division, but it takes out some of the guesswork that is normally involved. So for instance, if we wanted to do 363,612 divided by 628, okay, we write out our long division problem. The first thing that we need to figure out, how many times does 628 go into 3636? And we use Napier's bones to determine that. So here is 628 times 1 times 2 times 3 and so forth. One pitfall that people might fall into if they are not super duper familiar with this is they might look down, they might notice, okay, well, we need something that starts with 36. They might just look down the 6 column and see, oh, there's a 36, so it must be 6. And they would be wrong because this is not a number in the 3600s. This is actually a number in the 3700s because the 100s digit here is 7, not just 6. So that's kind of one pitfall, but otherwise, yeah, it takes out all of the guesswork of having to figure out like these little division problems. 628 goes into 3636 5 times, and we use the bones to see that 628 times 5 is 3,140, 3140. We do the subtraction like normal, and we just carry through the problem doing this exact same procedure. So it's still just long division, but we no longer have to like spend time figuring out these sort of like miniature division problems that are embedded in long division. The very last thing that I'll sort of mention really quickly is that Napier's bones could be used for calculating square roots. There's actually another rod, which I don't have here, I didn't write it out, but it was a square root rod, which would show the digits 1 through 9, and it would show their squares, the square of each of those digits. And the method for extracting roots using his bones it's a little bit more involved than the multiplication and the division was, and the reason for why it works is not nearly as obvious and direct as the multiplication and division ones. So I didn't incorporate that here, but if anybody is curious, there are videos out there for how that was calculated. It just involved the square root rod. So super duper cool stuff. But I wanted to go through all of that because Napier's logarithms is kind of, like I said, I think the more meaningful of his contributions. And it's something that I feel like it really deserves like a lot of explanation. I was sort of taken aback when I first got into all of this. I chose this topic just arbitrarily. I just randomly chose a topic. I thought, yeah, I know about logarithms. This shouldn't be that bad. And I was surprised. It actually was a little bit more difficult than I had expected. And as has been mentioned, our text kind of just really like rushes through everything that's involved, and it's fairly involved. So what I would suggest for you, one of the hard things that was hard for me was that I kept thinking about Napier, trying to think about Napier's logarithms in exactly the way that our logarithms work, and that was a mistake. So I encourage you for the next handful, whatever, 20 minutes or so that this takes me, to try to remove yourself from what you know about logarithms, and we're going to build up to Napier's logarithms. And there is still a relationship. Napier's logarithms, there's a difference, but Napier's logarithms definitely sort of set the stage for our modern logarithms. So the idea of his logarithms was once again similar to the idea of the bones, was how can I reduce multiplication of cumbersome numbers to just very simple addition and subtraction? And he actually wanted to do this to the end of multiplying trig numbers, which I'll talk about a little bit later. But for now, you can just think of it as how can I multiply two numbers and reduce that to just like a simple addition or subtraction problem. So Napier coined the term logarithm, which combines the two words, the Greek words logos and arithmos. Logos, our book says that logos translates to words. I've seen in other places that there are various translations, maybe something like reckoning number or ratio, something like that. And arithmos means number. So together, the term logarithm can kind of be thought to mean like artificial number, reckoning number, or a corresponding numbers. So Napier introduced the concept of all of this in his work Mirifici Logarithmorum Canonis Descriptio, which is translated as a description of the admirable table of logarithms, which was, he wrote it in Latin, was published in 1614, translated into English in 1616. Shortly after Napier's death in 1617, another one of his works was posthumously published and was titled Mirifici Logarithmorum Canonis Constructio. And the Constructio explains how the logarithms and the logarithmic tables of the Descriptio were formed. So Descriptio kind of introduces the logarithms, says how to use them. Constructio talks about sort of how it was all constructed. And so here's the idea. Like I said, I want to start from like the very bare bones and build up to Napier's idea of the logarithms. So it was already known to mathematicians at the time that in certain situations, multiplication problems could be reduced to much simpler addition problems. And this is really easily seen by looking at powers of two. So suppose we sort of listed out powers of two in this first row. And in the bottom, we listed out the corresponding power of two that corresponds to that number. So 2 to the 0 is 1, 2 to the first is 2, and so forth. Well, if we wanted to multiply two of the numbers in the top row, if we wanted to multiply two of the powers of 2, this actually can just be really easily reduced to summing the corresponding number, their exponents, and then doing sort of like a reverse lookup to see what number corresponds to that exponent. So for instance, 16 times 128 can be reduced to 4 plus 7. 4 plus 7 is 11. The number that corresponds to 11 to the 11th is 2048, which is 16 times 128. So 16 times 128 is 2048. So we've reduced not a terrible multiplication problem, but a multiplication problem that would involve a little bit of work. We reduced it to just summing two super duper easy numbers and looking up what the corresponding number is. Okay. And Napier thought about this same idea, but he kind of ran with it, and he thought about it in a novel way. And the way that he thought about it was he imagined if there were two lines, one of finite length, P naught Q, another of infinite length, L naught. And he imagined if there were points traveling across each of these lines, and these points would move at different speeds from each other. The point that moved across the infinite line just moved at a constant speed, whereas the point that moved across the finite line would move at a speed that was proportional, with some ratio, proportional to the distance that was remaining. And in this way, The two sort of points would form an arithmetic and a geometric sequence. So the point moving across the infinite line, it moves in any given time interval, like a unit of time, it moves the same distance every single time. It's a constant difference between these tick marks. The point that moved across the finite line, though, would move at a speed that was proportional to the distance that was sort of still left. So in a constant ratio relative to how much was left. So the ratio between subsequent intervals was the same. So that's how on the bottom this is an arithmetic difference, an arithmetic sequence because there's a constant difference between two values. On the top line, there is a geometric sequence because there's a constant ratio between adjacent values. So suppose that this ratio was 1/2. The idea is that, well, then when point L reaches the first tick, point P has traveled half of the distance of P naught Q. So P ends up over here. When L makes it to the second tick, P travels half of the distance of P naught Q. So it ends up here, and so on and so forth. And Napier actually defines his logarithm kind of with this idea. He says, okay, well, let's say that the logarithm of PQ, the distance that still needs to be traveled by P, the logarithm of PQ is equal to L naught L, the distance that L has traveled. So here he's creating this correspondence between sort of these ticks on these two lines. And this is one way of reducing a multiplication problem to addition. And here's kind of the idea, again, keeping with the notion that P travels half of the remaining distance. Here is what those sort of ticks look like. So P travels half the distance of P naught Q. Then P travels half of half the distance of P naught Q, and so on and so forth. So if we look at it, the corresponding logarithms, the logarithm of 1/2 would be 1. The logarithm of 1/8 would be 3. So if we wanted to multiply 1/2 times 1/8, this corresponds to the sum of 1 plus 3, which is 4. A reverse lookup, what number corresponds to the logarithm 4? Well, 4 corresponds to 1/16, which is 1/2 times 1/8. So 1/2 times 1/8 is equal to the reverse lookup of 1 plus 3, or the reverse lookup of 4, which is 1/16. So we've reduced multiplication to addition, but we've only done so if we're multiplying powers of 2. So this is super convenient if we're multiplying powers of 2, but what about anything else? And Napier wanted to simplify the multiplication of just about any number. And so he needed to take this sort of a step further. And the way that he did that was by recognizing that if the distance that P travels across the finite line is made really, 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 really small, then the result is that he has more of these numbers that can be multiplied and reduced to just like the addition. And so Napier chose for P to travel 1/10,000,000th of the remaining distance for every tick that L traversed. So, in other words, at every subsequent tick, P would have 1 minus 10 to the negative 7th of the remaining distance left to travel. So point P would still have 99.99999% of the remaining distance to travel. So it's just moving like a little bit each time. So over here, this table kind of illustrates what that looks like. So when L hasn't moved at all, when L naught L is just 0, then the length that P needs to travel is the full length, P naught Q. When L reaches the first tick, in other words, when L naught L is 1, then P will have traveled 1/10,000,000th of P naught Q, which means that the distance left to be traveled, PQ, is P naught Q times 1 minus 10 to the negative 7th. Then when L travels to the next tick, P travels 1 minus 10 to the negative 7th of the remaining distance. The remaining distance was the entry in the previous entry. So 1 minus 10 to the negative 7th times P naught Q times 1 minus 10 to the negative 7th, or P naught Q times 1 minus 10 to the negative 7th squared. And the pattern emerges that at each tick, PQ becomes p naught q times 1 minus 10 to the negative seventh raised to however many ticks L has traveled. But notice that for all natural numbers n, 1 minus 10 to the negative seventh to the n is less than or equal to 1. So in order to work with integers, which is what Napier wanted, he scaled the line p naught q to be a length of 10 to the seventh, which is really just the result of taking 1 minus 10 to the negative seventh and multiplying it by 10 to the seventh. So we arrive at this formula right here, where PQ, and it's just coming from this table over here, where we substitute P naught Q equals 10 to the seventh. PQ is equal to then 10 to the seventh times 1 minus 10 to the negative seventh raised to the L naught L. In modern terms then, Napier's logarithm can be defined as follows. So for any value x, the logarithm of x is equal to y if and only if x equals 10 to the seventh times 1 minus 10 to the negative seventh raised to the y power. And this is the big definition. This is Napier's big definition of his logarithm. This is how it's defined. That the logarithm of x is equal to whatever value y that satisfies this equation, where x is equal to this expansion. And this is just rewriting what we saw on the last slide, but now we're replacing PQ with x. The distance remaining, PQ, is now x, and the distance that L has traveled is now y. And this has this really nice characteristic that suppose we had two numbers, x1 and x2, which we knew what the logarithm of those numbers was. So the logarithm of x1 is y1, the logarithm of x2 is y2. If we multiply x1 times x2, we end up with, we're just multiplying these two expansions, rearranging terms, and using our modern, like this is written in our modern notation. This wasn't something that Napier wrote out, but just to see it in our modern notation, x1 times x2 ends up being 10 to the seventh times 10 to the seventh times 1 minus 10 to the negative seventh raised to the y1 plus y2. Now suppose that we had some big comprehensive table and we were able to look at this table and we found that there's some number x3, the logarithm of which was y1 plus y2. Well, then that means that x3 is equal to 10 to the seventh times 1 minus 10 to the negative seventh raised to the y1 plus y2th power. So in other words, x1 times x2 is equal to 10 to the seventh times x3. Super duper convenient, because 10 to the seventh just means take the decimal point of x3 and move it 7 times to the right, or add 7 zeros at the end of x3. So it makes it really easy to compute two values as long as you have this very comprehensive table. And the way that Napier set this up, that comprehensive table would require there to be, around 10 to the seventh or 10 million entries in a table, which is a crazy amount of work for a single person to do, or even for a team of people to do. But Napier, being a super duper clever guy, made a very astute observation. And it was essentially, in modern notation, it was this. So suppose that we define a sequence of values and we define them recursively, where I guess it doesn't even have to be recursively defined, where it's just x sub n is equal to 10 to the seventh times 1 minus 10 to the negative seventh raised to the n, where n is taken to be a natural number. Then x sub n plus 1 can be written in this same way, with n plus 1 as the exponent. But then that means we can sort of break up this block in the parentheses here to be 1 minus 10 to the negative seventh to the n times 1 minus 10 to the negative seventh. Well, notice that 10 to the seventh times 1 minus 10 to the negative seventh to the n, that is x sub n. So x sub n plus 1 is equal to x sub n times 1 minus 10 to the negative seventh, and distributing this x sub n, now we have x sub n plus 1 completely defined, just in terms of x sub n, the previous entry. So in this way, Napier was able to construct his table of values recursively, because what this is saying is that the subsequent value is the previous value minus that value with the decimal point moved to the left 7 places. So for instance, if x naught is 10 million, then x1 is 10 million minus 1 because 1 is just 10 million with the decimal place moved 7 digits to the left. So x1 is 9,999,999. X2 can be defined in the same way. Is x1 minus x1 with the decimal moved gives you x2, and then x3 can be created, and x4. So you can calculate everything completely recursively in this way. And that's what Napier did, at least for the first 100 of his values. And then he used a quote, and I'm taking this quote from another history of math book that I have. He used a quote, series of clever arguments that enabled him to interpolate the rest. And everywhere that I've looked, I've had a really hard time filling in the gaps of exactly how it was that he did this. My best guess is that he did this same thing. He did this for 10 to the negative 7th, and then he did the exact same idea using maybe 10 to the negative 5th instead, and then the same idea using 10 to the negative 3rd, maybe constructed various tables in this way and was able to cross-reference through the tables in order to fill in all the gaps. I'm not totally sure. It's been hard for me to find hard answers on that. But in any case, this process of constructing these log tables took Napier nearly 20 years to complete, and it has the obvious shortcoming that the tables are, since they're constructed recursively and implicitly, the accuracy of any entry relies completely on the accuracy of the previous entries. And Napier did make a mistake at one point in one of his entries. In his first edition, there was a mistake in one of his entries, which was subsequently caught and corrected in the later editions. So here's just a quick picture of what some of these log tables look like. And like I mentioned previously, these log tables were not constructed with the idea of being able to multiply any numbers at all. They were actually, the idea was to be able to multiply trig values. And so that's what this table is kind of showing. So I'm just going to read this really quickly from the book, our text. Napier chose P naught Q to be 10 to the 7th because he intended the table of logarithms to be used trigonometrically. It was the logarithms of sines and tangents that he calculated and tabulated in his Descriptio, and not the logarithms of numbers in general. So, and that's kind of what is being shown here. So the way that this is being read is that this shows each of these pages, like it shows various sine values and the logarithm of that sine value based off of a specific degree. So this is for the degree, for the fifth degree. And that's why on the left here, we can see the minutes from 0 to 30 and 30 to 60. So this shows every minute of 5 degrees, starting from 5 degrees all the way up to 6 degrees here. And what this is showing, the sine, and this is actually 10 times 7th, 10 to the 7th times the sine of the degree. So 10 to the 7th times the sine of 5 degrees is this 871,000 figure. The logarithm of this 871,000 figure is this 24 million figure. Then moving from the right, this is actually the complement of whatever degree we're looking at. So this would be the complement of 85 degrees, and that's why there's an 84 written down here. So it's 84 degrees, and in the minutes, 84 degrees and 60 minutes is 85 degrees, which is the complement of 5 degrees. The sine of 85 degrees is written right here. The logarithm of that sine is right here. And so what this is really showing is here's the sine of theta. This is the cosine of theta. Here's the logarithm of the cosine of theta. And this is useful because in the middle here, this actually shows the logarithm of the tangent of theta. Because log tan theta is log sine theta over cosine theta, which is log sine theta minus log cosine theta using logarithmic rules. So this is technically the logarithm of the tangent of theta. So that's how this book is to be read. Okay, so really quickly here, I just want to do make a couple more mentions, and then we'll look at like an example of how this works. So the first thing to point out is that Napier's logarithms don't actually work the exact same way that our modern logarithms do, for the reason that 10 to the 7th is equal to 10 to the 7th times 1 minus 10 to the negative 7th raised to the 0th power. So in other words, the logarithm of 10 to the 7th is 0. And the result of this is that the logarithm of a times b, two numbers a times b, is actually not equal to the logarithm of a plus the logarithm of b. So this is one place where it's very different from our modern logarithms. And to see why this is not the case, let's just come up with a couple of values, arbitrary values, a, b. So where the logarithm of capital A is lowercase a, the logarithm of capital B is lowercase b, and let's let the logarithm of 1 be lowercase k. So 1 is equal to 10 to the 7th times 1 minus 10 to the negative 7th to the k. And we can manipulate this equation to show that 10 to the 7th then is just, if we just divide this over, 10 to the 7th is equal to 1 minus 10 to the negative 7th to the negative k. Well, then multiplying a and b, we see that a times b is 10 to the 7th times 1 minus 10 to the negative 7th to the little a plus b, of course. But then there's this extra 10 to the 7th that is being factored into there. And we just found that 10 to the 7th is this 1 minus 10 to the negative 7th to the negative k value. So we can rewrite our formula in this way so that we can combine the 1 minus 10 to the negative 7th values so that they have an exponent of a plus b minus k. So capital A times capital B is this 10 to the 7th times 1 minus 10 to the negative 7th to the a plus b minus k. In other words, the logarithm of capital A times capital B is a plus b minus k, which is nap log a plus nap log b minus nap log 1. The result is that we can't actually calculate the logarithms themselves in the same way that we can compute modern logarithms. Like with modern logarithms, if you know the log of 2 and the log of 3, then just add those together and that gives you the log of 6. We can't do that in Napier's system. By the way, this is how I sort of calculated the sort of closed form formula for calculating naplog of x for any positive non-zero number. Comes out to this. And the other thing I guess I should mention is that our text actually they prove this same thing, that naplog AB is not equal to naplog A plus naplog B. They do it on page 362 in box 11.2, but the way that they do it involves calculus. I found this way to be more direct. And I took this from my other history of math book that I have. So that's where I got this. I didn't come up with this on my own, but I found this to be a more direct way than what our book did. Our book involved calculus, and it also involved a strange closed form formula for naplog x, which I actually kind of disagree with their closed form. I think it's more of an approximation. I think mine is more exact. I don't know, maybe I'm missing something, but in any case, this closed form formula can show that naplog of 1 is in the 161 millions, which is exactly why we can't calculate the logarithms in the way that we can, Napier's logarithms, the way that we can modern logarithms, because this 161 million forces this naplog A plus naplog B minus naplog 1, it forces it to be some number that is nowhere on our table and we can't use. But nevertheless, Napier did reduce multiplication and division to addition and subtraction. And here's the proof. We've kind of already seen the proof for the multiplication. So if we say that the naplog of capital M is little m, the naplog of capital N is little n, then capital M times capital N equals 10 to the 7th times 10 to the 7th times 1 minus 10 to the negative 7th to the m plus n. But this number right here, we can look this up. We can kind of do like a reverse lookup in Napier's log tables to figure out what value corresponds to, for what value the logarithm of that value is m plus n. Then 10 to the 7th times that number gives us m times n. Similarly, with m divided by n, the only requirement here is that little m is greater than little n, since we can't work with negative numbers in Napier's log tables. So this reduces to 1 minus 10 to the negative 7th raised to the n minus nth power, which again, just doing a reverse lookup shows us what number corresponds to this m minus n in the tables. And we just have to multiply by 10 to the negative 7th to account for how this 10 to the 7th is going away. The very last thing that I'll kind of show here before we do a super quick example is that the logarithms, Napier's logarithms, can also be used for square roots in certain situations. And here's one situation where his logarithms reduce the difficulty of finding the mean proportional of two numbers, which is that, so if we again have m and n defined in the normal way, taking the square root of their product, we have two of these 10 to the sevenths in there, so we can pull that out from under the radical, and this 1 minus 10 to the negative seventh, the exponents there are added to be m plus n. Using our modern exponent rules, then this square root is the 1/2, like the exponent's the 1/2. So we can push that in so that this becomes, the exponent becomes m plus n over 2. Again, doing a reverse lookup of m plus n over 2 gives us some number. We multiply that number by 10 to the seventh, and that gives us our mean proportional. Okay, so finally, just to see a quick example of how this works, here are some tables that I took from somebody named Dennis Regal, who I cited him on the next slide, by the way, but he has this incredible write-up of Napier's logarithms and all of this sort of stuff, and he has these tables here. So suppose we wanted to multiply these two ugly numbers, the one ending with 77 and the one ending with 62. If we wanted to multiply them together using Napier's log tables, we just look up those, find those numbers in the table and find their corresponding logarithms. So the logarithm of the 77 figure is 23. The logarithm of the 62 figure is 38. 23 plus 38 is 61. So it's this 9,999,939 figure. Moving the decimal place seven places to the right gives us the product. And similar with the division, we have to divide the smaller number by the larger in order for the exponents to work out, but it's the same thing. We just do 38 minus 23 gives us 15, and here's our answer multiplied by 10 to the seventh. Okay, and here are all of the references that I used. I hope that that makes all of this a little bit clearer than our book sort of made it, and I hope it was interesting. Thanks so much.